Live financial markets are hostile environments. Expose a rigid, unoptimized predictive model to this chaotic, high-pressure data stream, and the system shatters. There is a core misconception driving investment: the idea that generic generative AI and large language models can be applied zero-shot to asset management. Static LLMs are built for text generation, not mathematical reasoning. When forced into algorithmic trading, they tend to hallucinate calculations and overfit to obsolete historical data. In a live deployment, theoretical alpha is immediately eroded by three specific forces: model hallucination, execution latency, and market friction. Overcoming these forces requires moving away from static models in favor of brain-like architectures capable of genuine, real-time market cognition. Ultimately, surviving modern markets is not a text generation problem. It is a systems engineering challenge that requires a custom algorithmic architecture. To address this, we are going to outline how to build an AI-driven quantitative trading engine from first principles. This pipeline illustrates the necessary layers: feature engineering, neural topology, and API execution. Within the topology layer, specialized temporal fusion transformers and mixture of experts ensembles handle diverse data. Finally, the execution layer translates model outputs into hardware instructions at sub-millisecond speeds. This architecture integrates proprietary order patterns and timing signals, reducing reliance on noisy public data. Ultimately, this three-layered approach provides the exact structural framework necessary to map chaotic market data into clean, executable trading signals. Raw, non-stationary financial data cannot be fed directly into a neural network without causing extreme model instability. We must combine standard time-varying technical signals, like RSI and MACD, with behavioral on-chain metrics. This chart shows the raw spent output profit ratio, or SOPR, used to gauge investor profitability. Its highly skewed distribution requires a logarithmic transformation to smooth extreme volatility spikes. Finally, a z-score transformation standardizes the data into a zero-mean input vector. Certain behavioral metrics need different treatment. Realized cap HODL waves are strictly bounded between 0 and 1. We employ logit transformations for these bounded variables. This prevents the gradients from vanishing during the training process. Enforcing these mathematical normalization layers is essential to prevent the network from overfitting to market noise. Once the data is normalized, processing it across millions of subsystems creates a massive computational bottleneck for traditional dense networks. To solve this, we use a mixture of experts ensemble, replacing dense structures with specialized expert subnetworks. This equation defines the MoE architecture, using a probabilistic approach to aggregate specialized submodels. The gating function applies a softmax to assign specific weights, adaptively routing data only to the most relevant expert subnetworks, while the rest remain inactive. The routing mechanism functions like fluid dynamics, channeling computational power only into the specific subnetworks where it is required. This divide-and-conquer strategy allows the model to process institutional-grade volume without an exponential increase in latency. This topology ensures the model maintains its capacity for universal approximation, while the gating mechanism ensures inference remains computationally efficient. After routing, the data enters the core prediction engine, the Temporal Fusion Transformer, or TFT. The TFT is unique because it explicitly separates observed past inputs from known future covariates, such as technical indicators. Entering the TFT, data passes through the variable selection network for dynamic filtering. It then moves into gated residual networks, mapping non-linear relationships, before a temporal attention layer identifies long-term historical dependencies across the entire time series. Throughout this process, variable selection gates weigh the importance of every feature at every specific point in time. This dynamic weighting provides a layer of interpretability, offering insight into which specific features are driving the model's predictions. This level of transparency allows risk management teams to audit the model's behavior and better understand the logic behind specific algorithmic decisions. Even the most sophisticated predictive signal is useless if the infrastructure fails to execute it in time. The model's output, daily buy, hold, or sell signals, must be pushed through dedicated API endpoints before market conditions shift. This schematic shows the institutional requirements for execution. We are aiming for sub-45 millisecond latency with a throughput of at least 50 requests per second. Maintaining this requires managing multiple concurrent WebSocket connections to support the model's continuous, real-time learning loop. Relying on basic price data isn't enough. The system requires streaming depth 30 order book data to accurately capture live supply and demand dynamics. Theoretical alpha only becomes realized when it is physically translated into hardware-level instructions at sub-millisecond speeds. The final hurdle for any algorithm is market friction and taxation. As this ledger shows, a profitable trade is easily undermined by fees. High-frequency algorithms will trade a portfolio to zero without explicitly modeling tax erosion. You must account for 18% GST on brokerage, SEBI turnover fees, and the 0.15% securities transaction tax. The TFT and MOE architecture must internalize these friction thresholds, calculating the true expected value of a signal after all costs are deducted. A sustainable advantage is built by establishing a structural moat, combining proprietary data with a high-performance execution layer that retail systems generally cannot replicate. Success in institutional trading depends on the total integration of normalized data, dynamic neural topologies, and friction-aware execution.